Hi, dear all. I'm Kültigin Demirlioğlu, a PhD candidate in Oslo Metropolitan University. I'm going to present a study on seismic vulnerability assessment of a historic brick masonry building by fragility functions. This study presents a seismic vulnerability assessment of a unreinforced masonry building constructed in 1925 and registered in the Cultural Heritage List by Turkish Republic Ministry of Culture and Tourism. Experimental studies were carried out, including in situ and laboratory material tests and full-scale ambient vibration tests. Therefore, the obtained results were used for generating the numerical models of the structure and for final element model calibration. Nonlinear incremental dynamic analyses have been performed under 15 different earthquake records to determine the probability distribution of the seismic demand for each limit state of damage. Finally, vulnerability assessment was executed comparing the results obtained from the analytical fragility curves and empirical fragility curves. The building symbolizes a specific typology of the traditional Turkish historical building architecture in the early 20th century. The walls composed of solid clay bricks and Khorasan mortar, which is widely used local mortar in the construction of historical masonry structures in Turkey, and commonly includes hydraulic lime, kaolin, calcite, and refined Khorasan clay. The building has a brick arch floor system where the steel beams of IMP 180 are installed with an interval of 60 cm. Connection of intersecting walls and clamping between bearing walls and floor systems are in good condition. The 3D finite element model were generated with initial material properties firstly, considering homogeneous and isotropic material idealization. Shell elements with 4 nodes were used for modeling the bearing walls, and the slab were modeled with beam elements. The finite element model calibration was done based on the results obtained from operational model analysis and material tests. Initially, the response spectrum analysis as a linear dynamic analysis procedure was conducted on the 3D finite element model. This assessment comprised the evaluation of relative story displacements, drift ratios, and corresponding limit states described in the literature, because the literature proposes that the structural damages can be directly associated with interstory drifts. After performing the linear dynamic analysis, we detected that the front facade would govern the collapse state of the unreinforced masonry structure because higher drift ratios, thus more severe limit states obtained from the front facade compared to other sides of the structure. After the front facade of the building was determined as the most critical wall in terms of collapse as a result of linear dynamic analysis, a 2D equivalent frame model of the vulnerable facade was generated to simulate the nonlinear behavior and further study on vulnerability assessment. Equivalent frame method is a simplified method for performing nonlinear analysis. In this method, bearing walls are subdivided piers in gray and spandrels in red, where deformation and nonlinear response are concentrated, and rigid portions in black, which connect these deformable panels, as you can see in the figure. After the nonlinear model was established, incremental dynamic analyses were performed for comprehensive assessment of structural response from linear range to nonlinear range, leading to collapse. A set of ground motion records was selected advertently in accordance with the design spectrum and properly scaled to several levels of seismic intensity in order to enable the structure to cover the entire range of structural response under each seismic excitation. As a result of nonlinear analysis, force displacement curves were obtained as shown in the figure. For the readers interested in the whole work, you can find all the details regarding how nonlinear behavior was defined and how the numerical models were generated in our study. According to Eurocode 8 Part 3, the limit states of unreinforced masonry walls were determined, which correspond to the attainment of the global displacement capacity on the pushover curve. Limit state of limited damage is where the structure yields on the idealized pushover curve. Limit state of significant damage is equal to 3/4 of the top displacement capacity corresponding to total base shear. Limit state of near collapse is equal below 80% of the peak resistance of the structure. In this study, PGA values were used as intensity measure that characterizes the conditional probability of attaining a given damage state for a given hazard level. By scaling the PGA values, it's aimed at leading the structure to reach all limit states from yield point to collapse. For example, when the structure is induced by North Carolina ground motion with a PGA of 0.25 G, the structure will experience the limited damage limit state. When the PGA is scaled to 0.4 and almost 0.45 G, the structure will experience significant damage and near collapse respectively. Using the PGA values leading the structure to reach these limit states, the analytical fragility curves were derived by employing log normal distributions in calculations. The obtained fragility curves properly fitted the observed data as seen here. It showed that when the case study building is subjected to strong ground motions with the PGA values slightly more than 0.2 G and 0.4 G, it will experience limited and significant damages respectively with an exceedance probability of 50%. While a PGA of 0.45 G will be a sufficient intensity to reach the limit state of near collapse for the same exceedance probability. Later, these analytical fragility curves were converted to ones expressed in terms of spectral displacement as intensity measures for comparison with empirical fragility curves. Since the case study building is a type of two-story brick masonry building constructed in 1925, in literature, its taxonomy is equivalent to M5L, according to European building taxonomy, representing unreinforced masonry old bricks, and it's equivalent to URML, according to HAS 99, representing unreinforced masonry bearing walls. And finally, it's equivalent to B211, according to Istanbul building taxonomy, representing 4-story masonry building built in pre-1979. The fragility curves parameters of the empirical approaches were presented in the table, where ST is the median value of the log normal distribution of the intensity measure spectral displacement, and beta is the dispersion related to uncertainties in the seismic demand. In the figure above, obtained empirical fragility curves for the same taxonomy with the case study building were compared. As it can be seen from the figure, fragility curves derived from the HAS and Istanbul building taxonomy demonstrate relatively close behavior, and their spectral displacement demands for the limited damage underestimate the spectral displacement demands corresponding to limit state of near collapse by European building taxonomy. In other words, if the building is subjected to a spectral displacement demand of 20 mm, it will experience, as you can see, approximately 90% probability of collapse according to risk UE, whereas it's expected to reach the collapse probabilities 15% and 25% for the same level of the intensity measure according to Istanbul and Hazard building taxonomies. When considering the structural response of the case study building, based on the results obtained from the analytical fragility curves, the building reaches a complete collapse under earthquake shaking intensity of a 20 mm spectral displacement. As a result of the vulnerability assessment via the fragility functions derived from the analytical and risk UE-based empirical approaches, it can be concluded that they are more coherent in terms of the anticipated cumulative probabilities corresponding to intensity measures for the given damage levels. The article has presented the seismic vulnerability assessment of a historic brick masonry building through the empirically and analytically derived fragility curves. Derivation of analytical fragility curves requires demanding work due to incremental dynamic analysis. As an alternative to use of this computationally expensive procedure, the effectiveness of the empirically derived fragility curves has been questioned in order to see the possibility of their application in the vulnerability assessment of the case study type building, whereas in practice, they are utilized for the seismic risk assessment of a certain building inventory in a specific location. By means of the comparison of the results obtained from the empirical fragility curves, when the analytical fragility curve is taken as a reference, it has been observed that risk EU produces the closest result in terms of the anticipated cumulative probabilities for the given damage levels. For the masonry taxonomy, risk EU proposes well-defined fragility curve parameters since they are individually characterized and categorized into each masonry material in detail. While the other empirical approaches consider a larger range of masonry classification in general, risk UE, compared to the others, can be more convenient to be used for vulnerability assessment of the taxonomy of old brick masonry buildings representing the case study building. Thank you for listening.